Hello and good afternoon. My name is Nick Kucharewski, and today we're going to be talking about some of the trends that are happening in the next generation multi-tenant cloud network built for AI. So first I wanted to acknowledge so many familiar faces I see out there today. It's great to see some of you out there, familiar faces over the years, and it's really exciting to be working on this next generation of technology in the next-gen cloud network. So my colleague Lloyd Nguyen this morning talked about 2023 being an all-new beginning for cloud data center infrastructure. And of course, he was talking about the advent of Gen AI happening earlier this year and how it changes everything. In large part, everything that we did prior to this year and everything that we do from this point will follow a different vector. And in today's presentation, I wanted to talk about some of those specifics and the impact that it has specifically on networking infrastructure for the cloud and the products that we're building to serve these applications. We see two lasting impacts of the events of 2023. First, of course, the rapid expansion and acceleration of investment in AI accelerating technology. Right? We're going to see a continued expansion of all these new innovations happening within AI compute processing. But secondly, and perhaps just as important, is we're seeing a revolution in cloud connectivity infrastructure. The switches, the physical interconnect, including optics and copper, that actually allows you to connect and build up very large cloud networks built of these AI accelerators. So the focus of my talk today is going to be on the latter, on the new evolution in connectivity infrastructure. Through this presentation, we're going to start with first principles, looking at the applications running in the cloud themselves, a little bit about the evolution of how application architecture has evolved in the cloud network. Second, we'll talk about the impact of generative AI on these applications and why that will cause us to rethink the way we've done some of these things in the past. Third, we'll talk about the implications for networking infrastructure in terms of how we build those networks. And then finally, the future of networking equipment, both at the system level and the semiconductors that we're building to serve these applications. So to baseline this discussion, I want to step back 20 years. And really with a memory that I have. A couple years out of college, I visited a friend of mine at his house, and he had just started an internet company. Right? This was Internet 1.0, pre-cloud. And he was telling me about his business. He had just built up the front end for his web application. He was in the latest stages of building up his database and the logic to actually interface the two. And he was excited because he had just taken delivery of 2 brand new x86 servers that were sitting in shrink wrap on the floor in his room in the house he was renting. And he was really excited because soon he would actually be able to deploy those applications on that equipment, primary and redundant, with a UPS behind them. And I start here because it's amazing to note how far we've gone in 20 years. In this span, we've gone from hosting a web application as being something that you're literally running on hardware you've purchased to the infrastructure that we take for granted today. What has happened in the last 20 years? What are the changes that we've seen that have enabled this future we live in today? First of all is an evolution of the application from monolithic to microservices. In the beginning, we were all building web-based applications where all of the software was sitting in a single place. It was all running in a very tight loop, interacting with one another. And in some cases, the backend database was also running on the same physical hardware. Of course, we've seen a migration away from where the software has then been decomposed into microservices, where you have a UI, which is the front end, and then you have the application broken into different pieces that are running on different pieces of hardware. And then in another case, the database could be sitting behind that on still another piece of equipment. Those can be co-located, or they can actually be sitting very far away. So this makes a lot of sense. And at first glance, it says it looks great. But it relies on the architecture of the software to anticipate the fact that it's running on different pieces of hardware. So when you look at the performance of the whole application, you have to make sure that it will still run well since you've decomposed it into these microservices that are no longer co-located. First evolution. The second evolution we saw over the last 2 decades is going from single tenant deployments to multi-tenant cloud. This, at first glance, looks very simple. The idea was, at first, we would be running our web applications in a single building on a single set of equipment that I own. With going to multi-tenant cloud, clearly you have multiple users, each running their application within a single data center, which in many cases is hosted by someone else. Obviously, huge implications for the business and for the cost of actually starting a cloud-based application, an all-new business model, and an all-new industry unto itself. But when we think about it at a technical level, some of the implications are very significant. Running multiple users' applications on the same physical infrastructure means you have to have isolation. You need to have security isolation between those different customers and those applications. And then you also need to have performance isolation. Now, at first, this worked out fine, because if you're running a platform as a service where you're actually, the operator is running its own software and then hosting those services, it can obviously control the isolation on security and performance. If you're running infrastructure as a service, it gets a little bit more complicated, because you actually now have applications that could impose performance requirements on the network infrastructure itself. You have to take care to isolate those things. Nonetheless, all of these things proceeded very well, largely because the way these microservices were formed, the bandwidth that they were requiring, was actually well contained and can allow you to build this isolated multi-tenant environment. That's the second evolution. The third is the movement to hardware specialization. With the application broken apart, with it running on different pieces of hardware, you can now look to optimizing that hardware specific for the application. Instead of actually running all of the pieces of the application on a single piece of hardware, you're now relying on it operating on specialized compute nodes. This also worked really well because you can start to do cost optimization for each piece of hardware and then still provide the service to the user who is running in the cloud. But there is also some technical implications of this, in that you have to plan the build out of the cloud data center to make sure that you have the right pieces of specialized hardware for the applications you're running. And because you're running applications for your customers, it can be challenging to forecast your requirements in terms of what exactly you need in terms of the optimized physical hardware. Nonetheless, all of these transitions have happened very well. In the meantime, over the last 10 years, we had the development of AI, which occurred really rapidly over the last 10 years in terms of the new applications being developed, in terms of the way they would improve the applications that we were all enjoying. But here, there was a key simplifying assumption all the way up until last year. And that assumption was that AI was dedicated and placed on the side of that cloud network. You can think about it like a little supercomputer sitting off to the side, where you would make a request and then hear back what you need. And in that way, all of the assumptions about that cloud network structure that we had already talked about can continue to operate, and then you can separately build an AI architecture which is very well optimized for running that AI workload. And then you just have a transaction interface between them. This worked really well for large training workloads. It worked really well for applications which were intrinsic to the company itself. For instance, if you're doing a self-driving car and you need to have a lot of resources for that function, then this model worked just fine. Then the beginning of this year. With generative AI, we immediately saw this movement where natural language processing, where other Gen AI applications could then be seamlessly integrated into a very broad set of web-based applications. This was a very different way of thinking about AI. People started talking about all of the different services that they would be improving by adding Gen AI into those functions. People then started talking about what will be the cost impact of those improvements. How am I actually going to integrate that? Because everyone had been thinking of this with the previous model for the past 10 years. So this had a deep implication, obviously, for the opportunity, but also for the implications on the networking infrastructure and the compute infrastructure. Because all of those assumptions that I talked about that have happened over the previous 20 years have to be rethought. Specifically, when you take this infrastructure that we had built up for the last 20 years, which was built on microservices in a multi-tenant environment with hardware specialization, and then add to it AI with all of the different attributes that AI intrinsically brings, how would you then build a network that would optimize on that, that would provide services that would be isolated between users, that would actually allow you to pay as you grow, but deal with the problems of forecasting that specialized hardware? Those kind of issues need to be rethought in terms of the next generation AI infrastructure. And that's what makes it so challenging, but also so interesting for the next generation of equipment. So why is this hard? Why is it difficult to solve this? First of all, I think as we're all aware, AI data sets in many cases exceed the capacity of a single compute node. And this violates one of the initial premises of the migration to the cloud that we know today. When you have a single data set being spread across two compute nodes and you rely on extremely fast connectivity in order to complete those workloads, how can you actually predict the completion time? How can you actually characterize that application? How do you know you're going to be profitable? If you're a customer working in a multi-tenant cloud, how do you know that that's going to work well? If you now have a workload that's split across two compute nodes and you don't actually know what is the infrastructure connecting them, if you don't know how fast that will respond, the assumptions about predictable application performance have to be looked at again. Secondly, there's the challenge of raw performance. AI accelerators require interconnect speeds that are significantly faster than anything we've seen in the past, almost an order of magnitude faster than when we talk about a traditional compute server. Where you look at the types of devices we see in the industry today, you might see 400 gigabits per second on a traditional server class CPU versus a high performance accelerator requiring 3 terabits per second of I/O interconnect. So again, looking at some of those fundamental assumptions, you can no longer assume that all of these things would simply just scale. So that's what really drives the need for an all-new approach to this problem. So now, as we stand today, as a lot of the companies here today are looking at these challenges, these application challenges, to say, how can we preserve all of those foundational concepts of multi-tenant cloud infrastructure when you have pervasive AI and when that must be delivered as a key part of that service? And people talk about whether you maintain a front end and a back end network where you still continue to separate them but increase the throughput and reduce the latency between them, or do you do a converged infrastructure where you're actually mixing those resources? That has deep implications on how you plan the network and how you build it. So in terms of solving this problem at the network level, in our view, the network infrastructure for this future converged network requires 3 key attributes. Number 1, it needs to be fast. Number 2, it needs to be very predictable because you're now relying on it to deliver the same performance regardless of who's actually sharing that network. And third, it needs to be transparent because these operators are now closely engaged in provisioning applications across multiple nodes of their network. They need to see into the network itself to make sure those applications are provisioned appropriately so that they're delivering the desired performance. These have deep implications on the infrastructure and the equipment we build to serve that infrastructure. So first, fast, high throughput. That's good news. We've been working on high throughput for many years. So when you look at any infrastructure, when you're talking about accelerated computing, intrinsically you're talking about moving towards a much higher performance switch right to the edge of the network. A couple reasons for that. Increasingly, you will rely on doing more local switching, meaning interconnect in between the elements that are sharing that same rack. Number 2, it's extremely high performance, as we talked about. You can take advantage of statistical multiplexing between those devices so that you can enable very large bursts to enter the network. And you also really rely on driving a high bandwidth connectivity from those edge nodes to the switch itself, so that you can have more guaranteed performance for those elements. In other words, if you're splitting the workload outside of this rack, you want to make sure that the performance is comparable to if you had actually connected it inside the same rack. And that means you have to be able to provide very high burst speeds to those compute elements. Number two, low latency. As we talked about, splitting these applications but still delivering consistent services requires a low latency infrastructure. And we look at this in three specific components. One is single hop latency. The second is traversal time through the entire network, no matter where those elements are connected. And third is optimizing for queuing delay, which means how do you deliver low latency even when you have colliding traffic happening in the network? So first, single node latency. This is an area that Marvell with the Terralinks product line has been really focused on since the beginning. It's about building an architecture that can enable low latency and can work towards that goal of providing low latency under any conditions. Because that's really the vision, that's really what the operator would want to have. And here, when it talks about per hop latency, the architecture that you choose for the solution really matters. Because it's very, very difficult to start from a high latency architecture and then make it run fast. It's much easier to start with a fast architecture and continue to make it fast and continue to make it low latency. Second is optimizing traversal time. Here, one of the single biggest things that we can do within a data center network is to reduce the number of hops that traffic will take from its source to its destination. Makes sense. Less latency purely to propagate through, fewer congestion points to potentially collide with other traffic. And here, switch radix has a key contribution to how flat you can make the network and how few hops you can use in order to deliver that traffic to its destination. So increasingly, we see a focus on optimizing for these AI infrastructure architectures built on these wider, flatter networks, which require higher radix switches. And here, when you see a comparison, you see that, as an example, a 256 radix switch might require a network with 5 hops or 3 tiers to interconnect all of the nodes. Moving up to a 512 radix switch means that you can achieve the same total scale in 2 layers or 3 hops. So radix really has a big impact on this. Finally, the third contributor to latency or to low latency is optimizing queuing delay. This is all about how do you avoid congestion events, how do you react quickly to congestion events, and how do you give better handling for the lowest latency, most sensitive traffic within that network. In the limit, we see a future where operators may want to provision traffic with an understanding of how those workloads are distributed across those networks, which means traffic engineering. Moving away from a purely random or load distributed view of the cloud data center network towards one where an operator is taking an active role in engineering the traffic flows across the network so that you can get back to this original vision of providing deterministic performance no matter where those applications get placed. Following from there is adaptive network tuning. This is about telemetry, and then the operator taking decisions based on that telemetry to make adjustments, again, so you can get back to that performance closer to the ideal. The third is congestion control and congestion response happening within the switch. When these events occur, where does that information go? Can you react to that? How do you propagate that information? So there's a number of feature opportunities in terms of congestion control. And then finally, intelligence within the endpoint, where the endpoint itself can take action based on this feedback from the network, and you can try to actually resolve these issues at the source in an effort to improve performance. If you look at a lot of the talks this morning, A lot of the new innovations that are being introduced by various companies at today's conference are really focused on solving one or multiple of these 4 challenges. The key point I would emphasize is there is not yet any one key approach for how we're going to solve it. So flexibility is going to be key. A switching product that has a flexible, programmable pipeline with a lot of telemetry capability gives you that opportunity to implement new traffic engineering mechanisms, to work with the customer to enable the type of adaptive network tuning they're looking for, and to participate in end-to-end switch congestion control mechanisms. So without knowing exactly where the industry will end up, having that flexibility, having that strong telemetry is key. So that leads us into the final element, which is transparency. As I talked about, we now have a much more challenging problem where the workload itself can actually place burdens on the network that for an operator hosting a multi-tenant environment, they then need to mitigate. So this means that they have to have the ability to actively manage their network. And this comes down to orchestration. When you look at an operator, what is their strategy for provisioning workloads across the network, for then orchestrating those flows across the network, and then make those adjustments? This is really a key part of the next generation AI multi-tenant network. Here, in our view, open standards are absolutely essential to this migration. We've seen a number of announcements over the past 2 years about different solutions that are optimized for AI because they solve some of those problems that I talked about earlier in this presentation. However, in some cases, they do that with a proprietary mechanism. In our view, this is very dangerous because it does not necessarily provide the type of visibility that an operator would require to implement those type of orchestration functions that are specific to their workload, that are specific to their customers or the way that they run their business. So open standards would provide a way to provide the types of hooks that we're talking about in a way that the operators can build off of so that they can see what's happening in their network. Building from there, open standards would provide the opportunity for operators to differentiate or to extend based on those building blocks. The way we view all of these functions, they are building blocks that operators can use as tools in order to implement an end-to-end strategy for their broader network. They're looking at the endpoint, they're looking at the switch, they're looking at the orchestration software. And in many cases, the different operators' applications are so different that they may have a very different strategy on how they want those pieces to work together in order to provide their services. So open standards are essential to enable that differentiation. And the third, of course, probably goes without saying, those standards also enable supply diversity. And with a market growing as fast as what we're seeing now, we think that's going to be critical for the next 5 or 10 years. And OCP really provides a great venue, we're all participating here today, to enable that platform for developing new innovations, for developing platform architectures that really feed into the spirit of open standards and to enable all the benefits I talked about here today. In conclusion, I wanted to talk for one brief minute about the Marvell Teralinx product family. Teralinx is a clean sheet architecture that was built specifically to solve the challenges in next generation cloud networks. And we're really proud to say that in the product that we have built and are now sampling, we have really embraced a lot of the trends in the cloud network that we are seeing today. A lot of the attributes that I spoke of are well served with the Teralinx 10 product family. We have 51 terabits per second performance. We offer low latency under a broad set of packet types, of traffic types. We have a flexible programmable pipeline, which is proven not only for today's applications, but provides that future proofing so that you can deploy new strategies in the future. We offer a leading radix of 512 that allows those wider, flatter networks with fewer hops from source to destination. And we have sonic integration, which is another key element that enables that open ecosystem and really enables us all to work together in building and deploying these next generation solutions. We are demonstrating this in booth B13. Come by and have a look. 51 tera and low latency with sonic integration on display. So that concludes my presentation. I want to thank you all for your time today. Enjoy the show this week. Thank you.